Welcome to our presentation of Problem 5. This is Group 8, presented by Austin Stoker and Giovanni Jean. What are conductors, insulators, and semiconductors? Is a question you may be asking yourself before clicking on this video. You may have heard of them briefly in a conversation or read about them online, but never really understood what they actually are. What if I were to say to you that you actually do know and that you use them every single day of your life? Think of electricity as cars on a highway. Different materials let electricity flow differently, like some roads have 2 lanes and some have 6. Now think of conductors as an open road, just like this picture. Conductors are like a big open highway with a lot of space for cars to switch lanes and drive around. Cars, or the electricity, can move very freely and very quickly. Now in this case, picture insulators as a traffic jam or a closed off road. No cars are able to get through it all, or no electricity is able to flow through the material. Semiconductors are like this road with the traffic light. When the light is red, the school bus is not allowed to drive. Or picture no electricity is allowed to move through a material, just like an insulator. When the light turns green, the bus is allowed to drive, where the electricity is allowed to move through, and it acts like a conductor. This ability to control the flow of electrons is what makes your phones, computers, and radios work. This Venn diagram shows various common types of conductors, semiconductors, and insulators. Some common types of conductors are copper, silver, and aluminum, or many other types of metals, which create wiring, which is what conducts electricity throughout your house, as well as ocean water, which is full of salt, which is very good for attracting electricity and flowing electricity, which is why you do not want to be in the water during a thunderstorm. Some common insulators are rubber, wood, glass, and plastic. Rubber is very good for being in a thunderstorm because if you get struck by lightning on your car, the rubber will dissipate the electricity, as well as wood for when you're in your house. Glass and plastic are also used as coatings for wiring, and glass is used to be used as a coating as well. And some common types of semiconductors are transistors and diodes, which is your LED that we have here. And many semiconductors are made out of silicon and germanium. So the next thing we are going to look at is what are the different types of bonds? There are 3 primary bonds, and they are called ionic, covalent, and metallic. When you think of ionic bonds, think of this picture here, of this child giving an apple to his mother. And that is just like ionic bonding, where you have one atom giving an extra electron to another atom to complete a valence shell. And that is like NaCl, where one of the atoms is giving up its extra electron to make the other atom have a full electron shell to make both atoms happy. Because one of them is positive and one is negative, and they're going to attract very strongly. And so you want, when those atoms attract very strongly, they're going to give away their electrons. Covalent bonds are a little different. With covalent bonding, atoms are going to share electrons with each other to fill their outer shells. And an example of that would be silicon or diamond. Metallic bonds form a sea of electrons, which allows atoms to flow very smoothly and conduct electricity. These atoms in the sea of electrons are able to move smoothly and freely around these tightly packed positive nuclei. Secondary or weak bonds are not involved in the sharing or transfer of electrons, and that is what makes them much weaker. They're only there to help hold molecules together. And there are two types, van der Waals and hydrogen bonds. The van der Waals interaction is a weak type of bonding interaction. It is weak because electrons randomly shift and create positive and negative spots, just like a gecko climbing up a wall. Van der Waals interactions can be found in all kinds of materials, but they are strongest in non-polar molecules. Hydrogen bonding is the strongest type of secondary bond. They form when a hydrogen molecule is bonded to a very electronegative molecule like F, O, or N, which creates a very uneven charge like you can see in this picture. The O is very large, the oxygen is the one that is tugging on the two hydrogen molecules. And these properties of water, like high boiling point and their surface tension, are what come from hydrogen bonding. Energy band and band gap theory explains that electrons can only exist in certain bands, called conduction bands and valence bands, where conduction bands are the first partially unfilled bands, and valence bands are the last fully filled band inside of a molecule. Different types of materials have different band gaps. A band gap is the separation between the valence and the conduction bands. As you can see, materials with an overlapping band are metals, and they allow electrons to flow very smoothly, and they're conductors. And semiconductors have a much smaller band gap, and they can conduct energy if there's a current. And then an insulator has a much larger band gap, and there's usually no electrons being conducted. In the lab, we were able to determine that R equals rho times L over A, where R is equal to resistance, rho is resistivity, L is length, and A is area. Here's our potentiometer lab data, where we measured the length and the corresponding resistance on the potentiometer. And as you can see, resistance is proportional to length, because as the length got longer, the resistance got greater. And you can also see that resistance is proportional to the inverse of the cross-sectional area, which the cross-sectional area was constant throughout, so we did not measure that, but it can be easily explained by a larger cross-sectional area will allow more electrons to go through, so you will have a lower resistance, and vice versa, where a smaller cross-sectional area or a very thin wire will not allow as many electrons to go through, so you will have a larger resistance. And resistivity is also not present here because resistivity depends on the material. So something like copper will have a small resistivity and is very conductive. So if you put it all together, you get the equation R is equal to rho times L over A.
I was told to explain this following section like you guys are liberal art major students. So that being said, I just wanted to illustrate that there are a ton of different liberal art major students. So you'll also be getting a crash course of chemistry, just in case you missed it. Semiconductor. Semiconductors are materials in between conductors and insulators. If you remember from middle school, conductors are good at transporting heat and electricity throughout the material, and insulators are quite the opposite of that. So semiconductor, as the name implies, is semi. It is important in controlling the flow of electrons. I thought in order to clearly explain semiconductors and get this point across, it'd be good to revisit this topic of chemistry. Atoms, atoms and electrons. Atoms are the building blocks of matter. very small, very tiny, they exist. And within an atom, you have the neutron, the proton, and the electron. The electron is what we're really used to. Now, let's say that one of these electrons broke free. What would happen? There'd be a little hole right there where the electron previously was. Now, this is a cause and effect type of circumstance, and this breakaway electron is the conductive electron, and this hole is just what we know as a hole. Now, just a quick side, mobility, which we denote with mu, is just how easy electrons or holes move in said semiconductor. It would be wrong to talk about semiconductors without bringing up these two elements, silicon and germanium. Silicon is the most used semiconductor on the planet and is intrinsic, meaning that it's pure. I'll explain that later in the upcoming slide. And this is followed by germanium, which is extrinsic, which means that it's not by itself. As I talked about in the last slide, intrinsic is pure. There's an equal number of holes and conductive electrons, and it is naturally forming. Now, intrinsic means that it's doped. A good example of this, when I talked about germanium, germanium could be doped with phosphide, so germanium phosphide. And basically, it's about added impurities to control conduction. And you have two types, N-type and P-type. N-type adds electrons, P-type adds holes. All right, let's talk about a concept in semiconductors using LED lights. So when electrons move into a hole, it creates light, right? So when there's a bigger energy, there's brighter colors, and low energy is dimmer colors, and the dimmer colors can be so dim that you just can't see them. It can be infrared. The perfect example of this is gallium phosphide versus gallium arsenide. Gallium phosphide has a large energy drop, which emits a green light, but gallium arsenide has a low energy drop, which emits an infrared light naked to the human eye. All right, the following sections for my material science classmates. Now, this is a question you've been provided. I don't feel the need to kind of reread it as you all had the same question, so I'll just go to my solution. All right, here's my work. Feel free to pause the video and just check it out, see what you guys think. But one thing I wanted to add is that at 700 Kelvin, right, the Ni is going to drastically increase, which means conductivity is going to drastically increase, and resistance is going to drastically decrease because it is intrinsic. This is the second question, straight from Brightspace. Here's my work here, and I wanted to explain at 700 Kelvin, there's minimal changes per doping, per it being extrinsic. So conductivity changes slightly and resistance decreases also slightly.